If you stack the tallest building on Earth, the Burj Khalifa, 7 times, the uppermost spire would still be lost in the permanent night below 6,000 meters. That depth, a vertical marathon of crushing darkness, is the Hadal Zone, a realm more alien than the surface of Mars. Allow your breathing to slow as the gentle sounds begin, and let your body sink into the quiet. We are going somewhere. There is time. The lights can stay dim. In the Mariana Trench, nearly 11 kilometers down, snailfish glide past cameras, thriving where no vertebrate was expected to survive. Amphipods collected from the same depths carry microplastics, a quiet signature of human industry at the bottom of the world. Whole ecosystems, powered not by sunlight but by chemical seeps from the planet's interior, have forced a revision of the fundamental rules of life on Earth. The Hadal Zone is the deepest realm of the ocean, defined scientifically as that portion of the seafloor lying below 6,000 meters. It takes its name from Hades, the ancient Greek underworld, and it remains one of the most inaccessible and least understood environments on Earth. Only a handful of manned and robotic vehicles have ever ventured into this perpetual darkness, where pressures exceed 1,000 times that at the surface. Though the Hadal Zone conjures images of vast abyssal plains, it actually covers only about 1 or 2% of the total ocean floor. Yet within that sliver of area is compressed a staggering 45% of the ocean's entire depth range. The sea surface lies at 0, and the deepest known point plunges to nearly 11,000 meters. The Hadal Zone claims the full vertical sweep from 6,000 meters down to that ultimate limit, a band of more than 5 vertical kilometers. These extreme depths are not randomly scattered. They are almost entirely confined to a global network of 37 known Hadal trenches and troughs, each a wound in the Earth's crust where one tectonic plate grinds beneath another. The vast majority arc around the Pacific Ocean, tracing the ring of fire in a necklace of subduction. From the Peru-Chile Trench off South America to the Japan Trench in the northwest, they form a hidden geography of narrow, sinuous chasms. Among these, 5 trenches descend deeper than all others. The Mariana Trench, home to the Challenger Deep at nearly 11,000 meters, is the deepest of them all. The Tonga Trench in the South Pacific holds the horizon deep, plunging to almost 10,800 meters. The Philippine Trench reaches beyond 10,500 meters, while the Kuril-Kamchatka Trench and the Kermadec Trench both exceed 10,000 meters, their floors lying in a realm of absolute stillness. The morphology of these trenches is a critical part of their story. Unlike the wide, flat basins of the abyssal plain, Hadal trenches are typically V-shaped funnels, steep-sided and startlingly narrow for their depth. This shape is a consequence of the bending and tearing of the subducting plate, which creates a sharp, deepening crease. The walls can slope at angles that trap anything that drifts inside, making the trench a natural collector. This funnel-like geometry concentrates organic material, shaping the ecosystems that cling to the trench floor. Marine snow, the carcasses of dead plankton, and even larger falls of fish or marine mammals slide down the flanks, accumulating in the trench axis in far greater quantities than on the surrounding abyssal plain. The result is a narrow ribbon of relative abundance, where dense communities of amphipods, sea cucumbers, and xenophyophores thrive in the crushing quiet, their lives paced to the slow, steady rain of nourishment from the sunlit world above. In the winter of 1872, a converted Royal Navy corvette slipped away from Portsmouth on a mission without precedent. HMS Challenger had been stripped of all but 2 of her guns, her decks refitted with laboratories, specimen jars, and miles of hemp rope. For 3.5 years, she would crisscross the world's oceans, but it was in the spring of 1875 in the Western Pacific that her crew prepared to ask the most vertiginous question of all: how deep is the deepest part of the sea? On the morning of March 23, 1875, the ship lay over a featureless blue expanse now known as the Mariana Trench. The crew released a weighted line and waited while the hemp rope unspooled hour after hour, vanishing into the abyss. When the lead finally touched bottom, the tally showed 4,475 fathoms, or roughly 8,184 meters. It was a staggering figure, the deepest sounding ever recorded by human hands, though we now know it fell short of the true depth by more than 2 kilometers. The instrument that made this measurement was a triumph of Victorian engineering, a device known as the Bailey sounding machine. It employed a heavy lead weight, often around 150 kilograms, attached to a specially treated hemp line that was stretched and marked while wet, to ensure accuracy. A small tube driven into the weight would capture a plug of the seafloor sediment, bringing a physical sample of the abyss back to the light for the first time in history. That single plug of reddish clay, teeming with microscopic shells, was a revelation. It proved that life existed even in the most crushing darkness. Over the course of the voyage, Challenger's scientists would collect thousands of similar samples, and the monumental task of analysis would take nearly 2 decades. The resulting 50 volumes of reports, authored by an army of international specialists, meticulously cataloged the physics, chemistry, geology, and biology of the global ocean, effectively creating the discipline of oceanography and laying the first cornerstone of what would later be called hadal science. The deepest point they discovered was eventually named Challenger Deep in honor of the ship, a name that evokes a profound and gentle irony. The vessel that gave its name to the most remote spot on our planet sailed directly above it, measured its shadow with a plummeting line, and yet never truly witnessed it. The expedition possessed no camera capable of surviving the immense pressure, no submersible to carry a human eye into that eternal night. The ship's own perception of the deep ended at the end of a rope. So the name endures as a monument both to a pioneering achievement and to the vastness of the unknown that remained. HMS Challenger mapped the silhouette of a world it could only imagine, sketching the boundary of the hadal zone with simple tools and extraordinary patience. The trench it identified would wait nearly a century before human beings finally descended to its floor, a silent testament to the fact that every great discovery in the deep ocean begins not with a photograph, but with a question. Before the 1950s, the deepest parts of the ocean were imagined as a realm of eternal stillness. The crushing pressure, which could exceed 1,000 times the atmosphere at sea level, the complete absence of sunlight, and the near-starvation rations of food drifting down from above seemed to form an impenetrable barrier. Scientists expected the hadal zone, those trenches plunging beyond 6,000 meters, to be a vast, sterile desert on the ocean floor. This conviction had deep historical roots. In the 1840s, the British naturalist Edward Forbes proposed the concept of an azoic zone, a depth below which no life could exist. His initial boundary was set at a mere 300 fathoms, but the philosophical weight of his idea persisted for almost a century. The notion that the deep sea was a dead world cast a long shadow over the even deeper trenches, which were seen as the ultimate expression of that lifelessness. Early explorations of the abyssal plains, the soft floors lying above the trenches, had already begun to rewrite this narrative. The legendary Challenger expedition of the 1870s lowered trawls to depths of over 4,000 meters and brought back a bewildering menagerie of strange fish, sea cucumbers, and brittle stars. These communities were sparse, but they proved that life could endure far beyond Forbes's azoic boundary. Still, the hadal trenches, plunging nearly twice as deep, were considered a different story, a final unbroken barrier where the thinning pulse of life would simply cease. Scientists viewed the hadal zone not as a unique ecosystem, but as a mere extension of the abyss, growing ever more hostile with depth. The trenches were seen as passive catchments, funnels for a slow rain of detritus that was too degraded to sustain a resident food web. Because the physical conditions only intensified, the logical expectation was that the sparse populations of the abyssal plains would fade to nothing in the trench floor's deeper darkness and greater pressure. This assumption began to crumble when dredging technology finally reached the trenches in the 1950s. In 1951, the Danish research vessel Galathea sent a heavy trawl into the Philippine Trench and, from over 10,000 meters, retrieved a living sea anemone clinging to the mud. Subsequent expeditions by the Soviet ship Vityaz also hauled up animals from the deepest points, including holothurians and polychaete worms. The azoic myth was shattered at the very bottom of the world. These first glimpses revealed a world not teeming, but tenacious. The creatures were not lost strays from the abyss, but were specially adapted to the hadal environment, their bodies built for extreme hydrostatic pressure and their metabolisms attuned to the meager supply of food. The trenches were not lifeless, and they were not simply an extension of the abyss. They were a unique ecological province, and their discovery reshaped our understanding of life's resilience on Earth. At the seafloor of the Mariana Trench, the pressure reaches 1,086 bars. That is equivalent to the weight of 5 mid-sized cars pressing down on a single postage stamp. On the morning of January 23, 1960, the bathyscaphe Trieste descended into the silent darkness of the Pacific Ocean, carrying 2 men toward a place no human had ever seen. Jacques Picard, son of the vessel's designer Auguste Picard, and U.S. Navy Lieutenant Don Walsh, squeezed into the cramped spherical pressure capsule beneath a massive gasoline-filled float. Their target was the Challenger Deep, the deepest known point in the world's oceans, a trench nearly 11 kilometers below the surface. After a descent lasting almost 5 hours, the Trieste settled gently onto the seabed at a depth later corrected to 10,116 meters. The pressure outside the hull was over 1,000 times that of the atmosphere, yet inside the small sphere, the 2 men calmly observed the historic moment. As the Trieste stirred clouds of fine sediment from the seafloor, visibility fell to near zero, but not before the crew witnessed a fleeting glimpse of life in the Hadal zone. Walsh, peering through the thick viewport, spotted a small flatfish resting on the bottom, a creature resembling a sole or flounder. This observation would later become a subject of scientific debate, with many deep-sea biologists suggesting that what they actually saw was a sea cucumber, an organism far more common at such extreme depths. Alongside this enigmatic shape, Picard noted the presence of abundant shrimp, delicate crustaceans that drifted past the window, proving that even the deepest ocean trenches were not lifeless. The sight of any active animal in that crushing darkness was a quiet revelation. The Trieste remained on the floor of the trench for just 20 minutes before the crew decided to ascend. With the sediment reducing visibility and the temperature inside the unheated sphere dropping to just a few degrees above freezing, there was little to gain by lingering. Picard and Walsh ran through their checklists, shared a chocolate bar, and initiated the release of ballast, allowing the bathyscaphe to begin its slow rise back to the surface. The total time spent at nearly 11 kilometers deep was a mere third of an hour, a fleeting visit to a world that had remained hidden for all of human history. The mission was not without significant technical failures that would undermine its scientific return. During the descent, the outer plexiglass pane of the viewport cracked, though the inner pane held, and the indispensable echo sounder failed, leaving the crew uncertain of their exact altitude above the seafloor. The mechanical depth gauge indicated a reading of 11,521 meters, a figure later recalculated when it was discovered that the instrument had not been calibrated for the compressibility of the surrounding water. Most critically, the core sampler designed to collect sediments from the trench floor was rendered useless, and no water samples were successfully retrieved. The dive thus produced no physical specimens, no photographs, and no precise measurements of the environment. While the Trieste expedition proved definitively that human engineering could survive the full fury of the Hadal zone, it revealed almost nothing of scientific substance about the Challenger Deep itself. The voyage was a triumph of courage and metallurgy, a demonstration that the abyss could be reached, but the oceanographic community was left with little more than anecdotal reports of marine life. The absence of functioning instruments meant that questions about the trench's geology, chemistry, and biology remained entirely unanswered. Instead of opening a new chapter of deep-sea exploration, the dive quietly closed a book, leaving the Hadal zone as mysterious as it had been before the splashdown. 52 years would pass before another crewed vehicle descended to the same spot. It was not until March 2012 that filmmaker and explorer James Cameron piloted the deep-sea Challenger to the bottom of the Challenger Deep, finally bringing back high-definition video, sediment samples, and new scientific data. In that half-century of silence, the Trieste remained the sole human artifact to have touched the Earth's deepest point, its legacy one of extraordinary bravery that stood in isolation. The long interval underscored the immense technical and financial challenges of reaching such depths, challenges that had not diminished since that cold January day in 1960. In the blackness of the Western Pacific, nearly 11 kilometers below the surface, the Mariana Trench is home to a creature that defies expectation. Here, where the weight of the water column exceeds 1,000 atmospheres, lives the deepest vertebrate ever recorded. The species was formally described in 2017 as Pseudoleparus swirei, a pale, tadpole-like snailfish collected from depths between 7,966 and 8,076 meters. Its discovery rewrote the known limits for vertebrate life. A few years later, in 2023, a team from the Mindaru UWA Deep Sea Research Center lowered a baited camera into the Izu Ogasawara Trench south of Japan. In the silent footage, a small, solitary snailfish drifted into view, setting a new record at 8,836 meters. The fish moved with a gentle, unhurried ease, its translucent body perfectly at home in the freezing dark. That fleeting encounter pushed the boundary of vertebrate existence even deeper. Survival at such pressures hinges on a remarkable molecular adaptation. Snailfish tissues contain high concentrations of trimethylamine oxide, or TMAO, a small organic compound that acts as a chemical chaperone. Water molecules are forced against proteins with crushing intensity at depth, but TMAO stabilizes the delicate folds of these proteins, preventing them from denaturing. This biochemical shield allows their cells to function where ordinary tissues would collapse. The Hadal Zone, named after the realm of Hades, is a place of extreme energy scarcity, and this shapes the community of life that can endure there. Large, active predators like sharks are absent because their fast metabolisms demand far more food than the deep trenches can supply. Snailfish, by contrast, are built for economy. Their gelatinous bodies, reduced bone density, and sluggish lifestyles conserve precious energy, allowing them to thrive where a muscular hunter would starve. With no sunlight penetrating to these depths, the snailfish relies on a diet of small, protein-rich crustaceans known as amphipods. These scavengers swarm in the thousands wherever a carcass falls, and the snailfish glides through the swarms, picking them off. To locate prey in absolute darkness, it uses an array of sensory pores on its head and along its lateral line, detecting the faint vibrations and chemical signatures drifting through the still, cold water. Watching the snailfish in its deep sanctuary, one senses a life perfectly tuned to silence and stillness. It is a creature of profound simplicity, an unassuming testament to the resilience of vertebrate life. In the most forbidding environment on Earth, it has found a way not merely to survive, but to reign. The gentle snailfish now holds the key to understanding how life pushes back the boundaries of the possible. In the perpetual darkness of the Hadal Zone, where the seafloor plunges beyond 6,000 meters, a recent discovery has brought a troubling human signature to the most remote ecosystem on Earth. A new species of amphipod, Eurythanes plasticus, was formally described in 2020 from specimens collected in the Pacific Ocean's Mariana and Izu-Bonin trenches. Its name memorializes the polyethylene terephthalate microplastic fibers found entangled within the digestive tract of the holotype, a stark chemical record of surface pollution that has now permeated the deepest oceanic crusts. Amphipods are the undisputed cleanup crew of the Hadal trenches, their abundance and speed of response turning any deadfall into a fleeting feast. When a bait package is lowered to the seafloor and a camera clicks on, the first few frames reveal an empty, sediment-dusted plain. Within minutes, sometimes no more than half an hour, hundreds of these pale, shrimp-like crustaceans materialize from the void, swarming the bait in a frenzy of consumption that can strip a fish carcass to bone in a matter of hours. Their dominance is so complete that they often represent the only large scavenging fauna observed in the greatest depths. To thrive where the water column presses down with over 1,000 atmospheres, amphipods have evolved a cellular machinery of remarkable resilience. Their bodies manufacture high concentrations of small organic molecules, such as trimethylamine N-oxide, which stabilizes proteins against the crushing pressure that would collapse the delicate three-dimensional structure of enzymes in a surface creature. Lipid membranes in their cells are tuned to remain fluid rather than freezing into a rigid gel, and some species even possess specialized enzymes that work optimally only under the immense compression of the Hadal realm. The question of how these scavengers locate a meal across kilometers of lightless, still water is answered by an exquisite chemical sensitivity. A dead fish or squid drifting down from the mesopelagic leaves, an invisible plume of amino acids, amines, and other dissolved organic compounds that extends for great distances along the seafloor currents. Amphipods are equipped with an array of chemosensory hairs and antennae so finely tuned that they can detect these molecular traces at concentrations in the parts per billion range, following the chemical gradient with a certainty that guides them directly to the source. In a seeming paradox, the population densities of Hadal amphipods can rival or even exceed those of productive shallow water ecosystems. Trench axes act as natural funnels that concentrate the sparse organic rain from the overlying water column, delivering a surprisingly reliable food supply to the scavenging guild. The sheer number of individuals that appear at a baited lander, often hundreds per square meter, reveals a biomass that defies the notion of the deep sea as a uniformly empty desert, while their tissues steadily accumulate the chemical fingerprints of the ocean above. What amphipod bodies reveal about Hadal chemistry is both a natural ledger and a cautionary tale. Their fatty tissues store persistent organic pollutants, such as polychlorinated biphenyls and polybrominated diphenyl ethers, that have adsorbed onto sinking particles, making them unwitting recorders of industrial contamination. The discovery of synthetic fibers in Erythrines plasticus confirms that even the deepest living organisms are now part of the global plastic cycle, their very cells reflecting a chemical legacy that will outlast the quiet scavenging rituals of the Hadal night. Deep in the ocean's abyss, where sunlight never reaches and pressure would crush most life, dwells a giant that defies the very definition of cellular life. Xenophyophores are the largest single-celled organisms on Earth, with some individuals reaching a remarkable 20 centimeters in diameter. This is not a colony of cells working together, but a single sprawling cell, its vast interior a labyrinth of cytoplasm and countless nuclei. The first hint of these deep-sea giants came from the historic Galathea expedition of the 1950s, a Danish voyage that trawled the Hadal trenches. Among the gray ooze hauled from nearly 10 kilometers down, scientists found strange sponge-like clumps. They had unknowingly retrieved the first xenophyophores from the planet's deepest realms, an encounter that would take decades to fully understand. A xenophyophore does not simply exist on the seafloor. It constructs its own intricate world. It builds a fragile shell, known as a test, by gluing together sediment particles with a secreted organic cement. The creature selectively gathers sand grains, sponge spicules, and even the shells of tiny foraminifera, arranging them into elaborate structures of tubes, folds, and interconnected chambers that can resemble a delicate mud-colored brain or a spongy sphere. In the flat, featureless expanses of the Hadal plains, these giant cells become architects of the ecosystem. A single xenophyophore test creates a landscape of nooks and crevices, multiplying the complexity of the seafloor. This hard substrate offers a vital refuge for tiny crustaceans, worms, and other deep-sea life, making the xenophyophore a crucial ecosystem engineer that transforms a barren sediment stage into a teeming microhabitat. Among the most studied is Syringamina fragilissima, a species whose name speaks to its fragile, sandy form. It appears as a finely branched or spherical structure, pale and crumbly, like a weathered piece of coral. For years it was mistaken for a sponge or a protozoan colony, until the microscope revealed the astonishing truth. Hidden within its labyrinthine test was a single, continuous mass of protoplasm, a multinucleate cell that flows and branches through its self-made home. The sheer abundance of these single-celled giants in the deepest trenches was an entirely unexpected discovery. Hadal depths were long imagined as a sparsely populated, near-sterile zone, where extreme pressure and scarce food would forbid a thriving benthic community. Yet cameras and submersibles have revealed vast fields of xenophyophores, their densely packed tests covering the trench floors like a submerged meadow, forcing a profound revision of how life persists at the absolute limits of our planet. In the deepest reaches of the ocean, within the Hadal trenches that plunge to depths beyond 6,000 meters, life takes forms that defy expectation. Here, astonishingly, sea cucumbers, or holothurians, emerge as the dominant large animals. At certain Hadal sites, these soft-bodied echinoderms account for over 90% of the total biomass observed on the seafloor. Their silent, slow-moving herds blanket the abyssal plains in numbers that reshape our understanding of life under extreme pressure. These deep-sea holothurians are the great processors of the Hadal realm, feeding on the thin rain of organic matter that drifts down from the sunlit surface. This material, known as marine snow, accumulates as a fine, nutritious sediment in the trenches. Sea cucumbers ingest vast quantities of this sediment, extracting the last traces of organic carbon before passing mineral grains through their bodies. In doing so, they act as the living digestive tract of the deep ocean floor, constantly turning over the seafloor. Among the most frequently documented residents of these trenches are members of the genera Elpidia and Peniagone. Species of Elpidia, with their translucent, leaf-like bodies and a few stout tube feet, are often seen strolling across the trench mud. Peniagone species, equally iconic, navigate the abyss with a distinctive, almost gelatinous grace, their bodies adapted to the immense cold and crushing weight. Both genera, belong to the order Elacipodida, a group of sea cucumbers that have evolved specifically to conquer the deep. The dominance of these soft-bodied animals is a direct consequence of the physics and chemistry of the Hadal zone. Under such extreme pressure, calcium carbonate, the building block of shells and many skeletons, becomes highly soluble and tends to dissolve. Creatures with rigid, hard shells face a constant energetic cost to maintain their structures, while soft tissues are far more pressure-tolerant. This gives leathery, flexible holothurians a decisive advantage, allowing them to thrive where armored crustaceans and mollusks struggle. The extraordinary concentration of echinoderms on the trench floor reveals a food chain that is both efficient and surprisingly direct. The marine snow fuels a vast community of sediment feeders, which in turn support a sparse population of specialized predators, such as certain snailfish and amphipods. The sea cucumber's relentless processing of organic matter releases nutrients back into the water column and buries carbon, playing a critical role in the cycling of organic carbon in the deepest biosphere. Their presence is a visible measure of the slow, steady pulse of life that connects the surface to the abyss. Thus, the Hadal world, far from being a lifeless trench, is a realm quietly ruled by echinoderms. These ancient animals, with their simple yet perfectly adapted bodies, remind us that dominance in nature is not always about strength or speed. In the perpetual darkness, under the weight of 1,000 atmospheres, the patient processing of falling debris by a congregation of sea cucumbers sustains one of the planet's most remote ecosystems. It is a gentle, enduring dominance, played out over millennia. The Hadal zone's precise contribution to the global carbon sink remains unmeasured. Far beyond the reach of sunlight, in the crushing darkness of the Hadal zone, life assembles around a most unexpected energy source. Here, at depths exceeding 6,000 meters, cold seeps trickle fluids from the ocean floor that are rich in methane and hydrogen sulfide. These chemical compounds, rather than the photons of the sun, fuel entire ecosystems through a process called chemosynthesis. The creatures gathered at these seeps have never known daylight, yet they form some of the densest concentrations of biomass in the deep sea. The foundation of this hidden world rests on bacteria that perform a quiet alchemy. Free living in the sediments or nestled as symbionts inside the tissues of animals, these microbes oxidize methane and hydrogen sulfide to harvest energy. They convert that chemical energy into organic carbon, taking the place that photosynthetic plants hold in sunlit realms. In doing so, they create a living blanket, a bacterial mat, or an internal power source that sustains a chain of life in the absolute stillness of the trench floor. Two of the most profound examples of this phenomenon have been documented in the Western Pacific. In the Japan Trench, submersible dives have revealed active cold seeps at depths of around 7,000 meters, where chemosynthetic communities thrive in the axis of a subduction zone. Even deeper, within the Mariana Trench, the deepest point on Earth, researchers have observed shimmering seeps and dense biological assemblages near the serpentinized rocks of the forearc. These sites represent the deepest known cold seep communities on the planet, pushing the boundaries of where we understand life can persist. The first confirmation of such communities in the deep Pacific came in the mid-1980s, a discovery that reshaped marine biology. In 1984, the submersible Alvin descended to the Cascadia subduction zone off the coast of Oregon and encountered an unexpected oasis at over 2,000 meters. Scientists found vast fields of clams, tube worms, and thick bacterial mats clustered around methane-rich fluids seeping from the accretionary wedge. Prior to this, the deep ocean was assumed to be a barren expanse, dependent on the slow snowfall of organic debris from above. But here was proof that life could generate its own feast from the chemistry of the Earth itself. The organisms that inhabit these seeps carry their survival toolkit within their own bodies. Giant tube worms, for example, lack a mouth and digestive system entirely as adults, instead housing a specialized organ called a trophosome that is packed with sulfur-oxidizing bacteria. Deep sea mussels and vesicomiid clams also host symbiotic bacteria in their gills, and their tissues contain modified hemoglobins that can transport sulfide without being poisoned. Even the bacterial mats seen on the sediment surface are not simple films, but complex layered communities that can directly consume methane as it escapes the seabed. Each of these anatomical departures is a quiet testament to the power of an alternative metabolic pathway. These discoveries have profound implications far beyond our own ocean basins. The cold seeps demonstrate that a biosphere does not require starlight. It can be sustained entirely by the chemical entropy of a planet's interior. On ocean worlds like Europa and Enceladus, where vast liquid oceans lie trapped beneath kilometers of ice, similar serpentinization reactions could produce methane and hydrogen sulfide on a seafloor never touched by the sun. If life exists there, it may well resemble the communities we have found in the Hadal trenches, patiently oxidizing the planet's own chemical breath in a silent, endless night. In 2019, a camera sled glimpsed the pale, translucent form of a snailfish, Pseudolaparis yatabasorum, drifting over the seafloor at a record depth in the Mariana Trench. That single observation joined a quiet, decades-long sequence of Hadal surprises in which every expedition seems to discover life where it was not supposed to be. Each new encounter forces a careful redrawing of the limits once thought absolute, as organisms withstand pressures that dismantle complex molecules and navigate a world without light. The cumulative effect is a deep recalibration of the very idea of a habitable frontier, leaving the question not of whether life stops, but of how much further down it might still be waiting. To reach the deepest ocean trenches, science relies on two distinct types of subsea platforms. Remotely operated vehicles, or ROVs, are tethered to a surface ship by a cable that supplies power and transmits real-time video and data. By contrast, landers are autonomous, free-falling vehicles that carry instruments and cameras to the seafloor without any physical connection to the world above. In the Hadal zone, beyond 6,000 meters, landers become the platform of choice for a simple physical reason. A cable long enough to reach 11,000 meters would be impossibly heavy, prone to snapping under its own weight, and demand a ship so large that operations would be prohibitively expensive. Landers sidestep this entirely by making a solitary round trip, untethered. A lander begins its journey by sinking on a heavy ballast weight, typically a stack of steel plates, which carries it down at a steady walking pace. When its mission is complete, an acoustic command from the surface triggers a release mechanism, and the weights are left behind on the seabed. The buoyant frame, filled with syntactic foam, then carries the instruments and their precious data back to the sunlight. The cameras that document life in the trenches must survive pressures that would crush a conventional housing instantly. Engineers have developed flawless spheres and cylinders machined from titanium or high-strength ceramic, tested to withstand 12,000 meters of water. Inside these miniature vaults, the electronics sit in a bubble of air at 1 atmosphere, peering through a cone of sapphire glass. Materials science defines the working limits of every deep-sea machine. Fiber optic strands within an ROV tether allow a torrent of high-definition video and control signals to pass with minimal loss, but they too are fragile. Syntactic foam, a matrix of epoxy filled with millions of hollow glass microspheres, provides the non-compressible buoyancy that lifts both landers and submersibles back to the surface, remaining intact under the titanic squeeze of the Hadal night. On the aft deck of a research vessel, a lander deployment is a quiet ritual of precise choreography. The crew uses a crane to lift the streamlined frame over the rail and lower it gently into the swell, where it is released to begin its long fall. After many hours of waiting, a small figure bobbing among the waves is spotted by a lookout, often with the help of a radio beacon and a flashing strobe. The ship maneuvers close, a grapnel line is thrown, and the lander is winched back aboard, its hard drives filled with a glimpse of the planet's most remote frontier. In the pre-dawn darkness of a calm Pacific morning, a lone figure folded himself into a sphere of steel smaller than a household refrigerator. The deep-sea Challenger hung vertically from a crane, a torpedo-shaped submersible painted in vivid green and built in secret over 8 years. At its core lay a pilot sphere forged from a single block of steel, its interior diameter just 43 inches, a space so tight that its occupant could neither stretch his legs nor fully extend his arms. The sphere's walls, a full 2.5 inches thick, were calculated to withstand the 16,000 pounds per square inch of pressure waiting at the bottom of the Mariana Trench, a force that would crush a conventional submarine like a tin can. On the morning of March 26, 2012, James Cameron rolled the submersible's hatch shut and began his descent into the Challenger deep. The journey downward took 2 hours and 36 minutes, a silent, darkened plunge through water columns few humans could imagine. Inside the sphere, the temperature dropped to near freezing. Condensation dripped from the ceiling, and the only light came from the glowing instrument panel. As the depth gauge ticked past 10,000 meters and finally settled at 10,198 meters, the submersible kissed the seafloor with a soft puff of sediment, and Cameron became the first person to visit the deepest point on Earth alone. What he saw through the thick acrylic viewport was a landscape of astonishing stillness. The seafloor stretched away in all directions as a flat, beige plain, featureless and rolling gently into a gray haze. There were no rocky outcrops, no deep-sea corals, no giant squid or fish. The surface was a fine, silty ooze that resembled an empty desert floor, undisturbed except for the slow rain of marine snow. Cameron later described the Hadal Zone as profoundly lunar, a place where the absence of visible megafauna was so complete that it felt almost sterile. Within 90 minutes of arrival, the mission's scientific ambitions suffered a serious blow. A hydraulic fluid leak had disabled the manipulator arm and the mechanisms for deploying bait and collecting sediment cores. The sampling tools that were meant to return biological treasures from the trench hung useless. Yet the battery-powered array of high-definition cameras and enormous LED lights continued to function flawlessly, documenting the seafloor with a clarity never before achieved. The pilot was forced to shorten his stay, and after roughly 3 hours on the bottom, he jettisoned the ascent weights and began the long ride back to the surface. Despite the mechanical failures, the dive did not return entirely empty-handed. The submersible's passive sediment traps, which had been collecting particles throughout the descent and bottom time, survived the ordeal and brought back a small cache of the finest sediment ever retrieved from the deep sea. Water samplers collected the planet's deepest seawater, and the plankton traps captured a faint microbial haze. Later analysis of these samples revealed a sparse community of piezophilic bacteria and archaea, organisms that thrive only under the crushing pressure of the Hadal Zone, but the haul was a whisper compared to the roar of scientific possibility that had been planned. In the end, the dive's most enduring legacy was not biological, but mechanical. The deep-sea Challenger proved that a single individual could be carried to the extreme depths and back using a vertical, lightweight design, a revolutionary syntactic foam, and a pilot sphere of unprecedented strength. The mission advanced materials science, camera systems, and lithium battery technology far more than it expanded the catalog of life. This is why Cameron himself, reflecting on the silent, barren plain he had witnessed, called the Hadal Zone the most desolate place on Earth. The phrase was not a lament, but a quiet statement of fact, a reminder that the deepest trenches are vast, empty, and perhaps the most alien environment our planet has to offer. The Five Deeps expedition was conceived with a singular and audacious ambition: to send a human being to the deepest point in each of the planet's 5 oceans. Spearheaded by explorer and former naval officer Victor Vescovo, the mission aimed to systematically conquer the Atlantic's Puerto Rico Trench, the Southern Ocean's South Sandwich Trench, the Indian Ocean's Java Trench, the Pacific's Challenger Deep, and the Arctic's Malloy Deep. To make this possible, a submersible of unprecedented capability was required, and the result was the DSV limiting factor. Built by Triton submarines from a titanium alloy sphere, rated to withstand the immense pressure of full ocean depth, this vessel would become the first commercially certified submersible capable of diving repeatedly to any depth on Earth. On the 28th of April 2019, the expedition reached a defining moment in the Western Pacific. Victor Vescovo piloted the limiting factor into the silent darkness of the Challenger Deep, a realm within the Mariana Trench where the water column presses down with over 1,000 times atmospheric pressure. The submersible's multi-beam sonar and precision pressure sensors, calibrated for temperature and salinity, recorded a new verified depth of 10,928 meters. This measurement, slightly deeper than previous records, was not a dramatic overhaul of the seafloor map, but a meticulous confirmation that quietly reset the baseline for the deepest known point of our planet's crust. While the titanium hull kept the human occupants safe, a trio of unmanned landers named Scaff, Closp, and Flare descended alongside to gather the biological treasures of the Hadal Zone. These autonomous platforms, equipped with baited traps and sediment corers, returned with amphipods, which are shrimp-like crustaceans that thrive in the trenches, and delicate sea cucumbers that move across the abyssal ooze. At Challenger Deep, the landers retrieved the familiar amphipod Hirundalea gigas, a creature that secretes an aluminum-based gel to shield itself from predators, along with sediment samples teeming with microbial life uniquely adapted to the crushing pressure and frigid cold. The expedition's northernmost objective, the Malloy Deep in the Arctic Ocean, yielded a particularly ethereal surprise. As the lander's cameras peered into the gelid water column, they glimpsed a small, translucent fish moving with a gentle, undulating rhythm. Upon closer inspection and recovery of specimens, scientists confirmed it was a new species of snailfish, a member of the Liparidae family with a tadpole-like body and a skeleton adapted to the extreme pressure. This discovery marked the first record of a fish living at such depths in the Arctic, extending the known range of hadal vertebrates and adding a pale, ghost-like resident to the catalog of life in the deep. Prior to the 5 deeps, the logistics of reaching the hadal zone were dominated by a handful of national submersibles that required immense support ships and lengthy maintenance cycles, often limiting them to a single dive per expedition. The limiting factor changed this calculus entirely. Its design, incorporating a new type of syntactic foam for buoyancy and a hull that could be tested repeatedly without fatigue, allowed it to be deployed from a compact mothership, the DSSV pressure drop, and to dive day after day. This shift from a rare, almost ceremonial event to a repeatable, reliable scientific operation meant that researchers could now plan systematic transects and time series studies at full ocean depth. The quiet revolution of the 5 deeps lies not in a single record, but in the toolkit it bequeathed to marine science. The expedition's high-resolution mapping of more than 1 million square kilometers of unmapped seafloor, combined with the proven reliability of the DSV limiting factor, opened the hadal zone to a wider community of researchers. The submersible has since carried scientists on multiple follow-up missions, such as the Ring of Fire expeditions, transforming the deepest trenches from distant, almost mythical places into accessible laboratories where the planet's final biological frontiers are slowly, patiently illuminated. In the southern winter of 2017, a research team lowered traps into the Kermadec Trench and retrieved hundreds of small amphipods from the cold, crushing darkness 10,000 meters below the surface. When their fatty tissues were analyzed, the results showed unusually high concentrations of persistent organic pollutants, specifically polychlorinated biphenyls and polybrominated diphenyl ethers. These industrial chemicals, long banned in many countries, had apparently sunk through the water column and accumulated in the lipid-rich bodies of the deepest living scavengers. The discovery forced a reassessment of how efficiently the ocean's deepest basins can concentrate contaminants that were never meant to reach them. A solitary lander descending into the Challenger Deep in 2018 captured a sequence of images that stopped the control room cold. Drifting across the seafloor at nearly 11 kilometers depth, a single plastic shopping bag stirred softly in the current, its manufactured shape unmistakable against the ancient sediment. The sighting was logged in the Deep Sea Debris Database, adding a stark data point to the growing evidence that human refuse has penetrated the most remote and inaccessible ecosystem on Earth. It was no longer a question of whether plastic reaches the hadal zone, but how much of it already resides there. When scientists began analyzing sediment cores from multiple hadal trenches, they found microplastic fibers in every sample, often in quantities that exceeded those recorded in heavily contaminated coastal surface waters. The fibers, many of which were synthetic cellulose from textiles, were concentrated by the same funnel-like topography that directs organic detritus into the trenches. Their presence at such densities revealed that the deep seafloor acts as a terminal sink for the invisible fragments shed by modern life, accumulating them in a place once imagined as pristine. The Hades program, which ran from 2014 to 2017, brought together an international team to study the food webs of the Mariana and Kermadec trenches using baited cameras, landers, and remotely operated vehicles. For the first time, researchers documented the complete community structure, from the swarming amphipods that strip whale carcasses to the snailfish that patrol the upper hadal slopes. Stable isotope analysis traced the origin of their energy back to surface plankton, confirming that even the deepest life depends almost entirely on a slow rain of organic matter from the sunlit world. These observations have forced a significant revision of global carbon cycling models. Previously, the hadal zone was considered a passive repository where organic carbon settled and was buried over millennia. But direct measurements of microbial respiration in trench sediments revealed biodegradation rates that are orders of magnitude higher than predicted, indicating that a substantial fraction of the carbon reaching these depths is rapidly metabolized and returned to the water column. The models now account for the trenches as dynamic hotspots of biological activity rather than stagnant depressions. Each expedition into the Hadal Zone returns with a fresh set of measurements that quietly redraw the boundaries of what we think we know. The discovery of pollutants in the tissues of the deepest fauna, the sighting of a plastic bag in the ocean's deepest point, the ubiquity of microfibers in the sediment, and the revelation of unexpectedly active food webs all tell a single, accumulating story. The deep sea is not a remote void disconnected from the surface, but a tightly coupled extension of our own planetary system, faithfully recording every choice we make on the land and in the air above. Far below the sunlit surface, where the ocean floor plunges into narrow, abyssal scars, a quiet but globally significant process is at work. These Hadal trenches, the deepest reaches of the sea, function as powerful carbon sinks. Organic matter, much of it originating from surface plankton blooms, settles continuously across the ocean. On the vast abyssal plains, this marine snow often drifts slowly and may be consumed or respired before reaching the sediment. But near a trench, the topography itself intervenes. The sheer, steep walls of a trench act like a geological funnel, capturing organic particles that would otherwise be suspended in the midwater column for decades. Gravity pulls this material downslope in slow, inexorable flows of sediment, concentrating it from a much wider catchment area into the narrow axial valley. This process, known as sediment focusing, dramatically shortens the journey of organic carbon to the seafloor. What might have been recycled by microbes in the water column is instead entombed rapidly in the deep, cold, and oxygen-limited sediments of the trench floor. The geomorphology of a trench is uniquely suited to trapping carbon. The V-shaped cross-section and the frequent occurrence of subduction-related turbidity currents sweep material from the surrounding abyssal hills and even from the continental slopes directly into the Hadal Zone. These flows can transport vast amounts of terrestrial and marine organic carbon in a matter of hours, bypassing the slow, inefficient rain of individual particles. The result is a highly efficient delivery system that concentrates organic debris from an area many times larger than the trench itself, packing it into a narrow, deep repository. When scientists began to measure the carbon burial rates in these environments, the numbers were striking. Studies of trenches like the Japan Trench and the Atacama Trench have revealed that the rate of organic carbon accumulation per unit area is up to 19 times higher than on the surrounding abyssal plains. The sediment here is not just a thin dusting of particles, it is a thick, carbon-rich layer accumulating at a pace that defies the presumed slowness of the deep sea. This high burial efficiency is driven by the rapid sedimentation rates and the low temperatures, which slow down the microbial decomposition that would normally release the carbon back into the water. The most startling revelation, however, concerns the scale of this phenomenon. Recent research has shown that Hadal trenches, which cover less than 0.25% of the global seafloor, are responsible for a disproportionately large fraction of the ocean's total organic carbon burial. Some estimates suggest they account for nearly 2% of this burial, a figure entirely out of proportion to their surface area. This means that these narrow, seemingly isolated cracks in the Earth's crust are hotspots of carbon sequestration, punching far above their weight in the global carbon cycle. This discovery forces a reassessment of the ocean's carbon budget. For decades, global climate models operated without accounting for the Hadal carbon pump, effectively overlooking a direct and permanent pathway for carbon dioxide removal from the atmosphere. The recognition that trenches are not just passive repositories but active, efficient burial grounds for organic carbon adds a vital new piece to the puzzle of how our planet regulates its climate. Understanding the full rhythm of this deep sea engine is now essential for predicting the long-term fate of anthropogenic carbon in a changing world. We have likely described only 10 to 15% of the animal species that live in the Hadal Zone, the deepest realm of the ocean stretching from 6,000 to nearly 11,000 meters. This means that for every creature we have named, there may be 5 or 6 more waiting to be discovered in the cold, crushing darkness of the trenches. The true scale of life in these abyssal plains and fractured subduction zones remains an open question, a vast biological census barely begun. The act of simply collecting a Hadal organism intact is a profound engineering challenge. Animals that thrive under pressures 1,000 times greater than at the surface often depend on that pressure to maintain the shape of their proteins and cell membranes. When brought to the surface, their tissues can rupture, their enzymes cease to function, and delicate gelatinous bodies dissolve into a formless mass. Even when a sample survives the ascent, the risk of contamination from shallower water during the long winch journey is high, and the final sample size from a single lander drop is often just a few precious individuals. A new window into this hidden world is opening through environmental DNA, or eDNA, which captures the genetic fingerprints left behind by organisms as they move, feed, and decay. By filtering water drawn from the Hadal water column, scientists can now detect sequences of DNA that match no known species in any database. These ghost lineages hint at a rich diversity of bacteria, archaea, and eukaryotic life, including tiny soft-bodied animals that might never be seen by a camera or captured by a trap. The water itself is becoming a library of what exists below, even if the organisms themselves remain invisible. High above the trench floor, acoustic surveys are revealing a surprisingly active mid-water community that connects the shallower ocean to the Hadal realm. Shipboard sonars can detect dense layers of organisms, from small crustaceans to unknown fish, that migrate vertically each day. Some of these layers descend well into the Hadal zone, and their echoes suggest the presence of animals with gas-filled swim bladders, a feature long thought impossible at such depths. These acoustic signatures are providing the first population estimates for species that never appear in nets or traps. The Hadal zone likely contains a concentration of unique species unmatched by any comparable volume of shallow water. Each trench is an isolated evolutionary theater, separated from the next by hundreds of kilometers of abyssal plain, and from the sunlit world above by a column of near-freezing water. The combination of extreme pressure, sporadic food supply, and long-term isolation has driven the evolution of endemic life forms that exist nowhere else on Earth. A single trench can have a proportion of species found only there that rivals the endemism of an ancient island archipelago. This profound biological frontier carries a quiet but urgent message for conservation. The deep sea is no longer beyond the reach of human industry, with plans for deep-sea mining, the persistent rain of microplastics, and the slow creep of climate-driven changes in oxygen and temperature. Were we to lose a species unknown to science, we would lose not just a name, but a unique evolutionary solution to life's most extreme challenges. The Hadal zone, still largely a mystery, reminds us that our planet's catalog of life is far from complete, and that what we have not yet found may be of immeasurable value. The Hadal zone, the deepest realm of the ocean, is defined by a series of trenches that plunge to depths exceeding 6,000 meters. All 5 of the world's major Hadal trenches, the Mariana, Tonga, Kermadec, Philippine, and Japan, are situated along active subduction zones. Here, one tectonic plate steadily grinds beneath another, creating the dramatic topography that defines these environments. Subduction is not a smooth process. The immense friction between the colliding plates occasionally releases in violent earthquakes, which can destabilize the steep trench walls. These seismic events trigger dense sediment avalanches known as turbidites, powerful flows that cascade down the slopes and sweep organic matter from shallower waters into the trench floor. This sudden delivery of carbon provides a vital food source for the organisms living in the nutrient-poor abyss. The 2011 Tohoku earthquake off the coast of Japan provided a rare glimpse into how such events reshape the Hadal landscape. The magnitude 9 quake and its aftershocks caused massive slumping of sediment along the Japan Trench, remobilizing ancient deposits and exposing fresh rock surfaces. Subsequent investigations revealed that the seafloor had been fundamentally altered, and the composition of microbial and meiofaunal communities shifted in response to the new physical and chemical conditions. Beyond the dramatic pulses of sediment, the geological engine of subduction also drives a quieter, pervasive circulation of fluids. Seawater percolates down through the porous sediments of the trench, where it is heated by the underlying plate and chemically enriched by reactions with the surrounding rock. This hydrothermal circulation then returns to the seafloor, carrying dissolved minerals that can nourish chemosynthetic life, creating isolated oases of biological activity driven by the Earth's internal heat. These forces, from catastrophic turbidites to slow hydrothermal venting, mean that the biological communities of Hadal trenches are subject to periodic disturbance. A major earthquake and its aftermath can effectively reset the ecological clock, wiping out established assemblages and initiating a new cycle of colonization. The rate at which life recovers, the sequence of returning species, and the resilience of these deep ecosystems remain fundamental uncertainties, an open question that scientists are only beginning to explore. Studying the recovery dynamics of these remote communities is a formidable challenge, requiring long-term monitoring at depths that are extraordinarily difficult to access. Yet it is precisely this interplay between geology and biology that defines the Hadal world. Far from being a static abyss, the trenches are a dynamic mosaic of destruction and renewal, shaped by the restless movement of the planet itself. The next generation of Hadal exploration is being shaped by autonomous vehicles that sever the tether to large surface ships. Engineers are now testing untethered submersibles like Orpheus, a shoebox-sized robot developed by the Woods Hole Oceanographic Institution, designed to withstand the crushing pressure of the ocean's deepest realms while navigating independently from a small inflatable boat. These vehicles can be programmed to descend to a trench, map the seafloor, collect samples, and return to the surface without ever needing a mothership on station. This innovation promises to transform the pace and cost of Hadal science, making it possible to conduct frequent, targeted missions in the most remote parts of the planet, even from a coastal village. Environmental DNA is opening a new window onto the life that drifts invisibly above the trenches. By collecting water samples from discrete depths and filtering them for traces of shed skin, scales, and mucus, scientists can now detect the genetic signatures of organisms that might never be caught in a net or seen by a camera. A single liter of water from the Hadal pelagic zone can reveal a hidden community of gelatinous salps, migrating lanternfish, and elusive crustaceans, building a census of biodiversity without ever disturbing the animals themselves. These eDNA surveys are proving that the water masses above the deepest seafloor are far from a biological desert, instead harboring a dynamic and previously overlooked assemblage of life. The International Treaty for the Protection of the High Seas, formally adopted in 2023 under the United Nations Convention on the Law of the Sea, will fundamentally alter the framework for Hadal research. Much of the Hadal zone lies in areas beyond national jurisdiction, and the new agreement establishes a mechanism to create marine protected areas and mandates environmental impact assessments for activities that may cause substantial pollution or harm. For the first time, a scientific expedition planning to sample a trench in international waters may need to submit its protocols for review to ensure they do not inadvertently damage a fragile ecosystem. While this introduces a new layer of administrative oversight, it also offers a historic opportunity to embed conservation principles into the very first wave of systematic Hadal exploration. Full genome sequencing of Hadal organisms has revealed a remarkable story of convergent evolution under extreme pressure. The genome of the Yap Hadal snailfish, for instance, shows multiple copies of genes responsible for producing trimethylamine N-oxide, a molecule that stabilizes proteins against the distorting effects of immense hydrostatic pressure. Across different lineages, from amphipods to holothurians, entirely unrelated species have independently hit upon the same molecular solutions, such as specific amino acid substitutions in key enzymes and the enhanced expression of heat shock proteins to maintain cellular integrity. The pressure of the deep sea appears to be a powerful evolutionary filter, shaping life's biochemical toolkit in predictable and repeatable ways. A profound open question that will define the coming decade is simply this: how much life do these trenches hold, and how many species remain undescribed before we even attempt to catalog them? Some estimates suggest that perhaps 90% of Hadal invertebrates are new to science, with each expedition to a new trench returning a wealth of novel forms. Compounding this urgency is the growing evidence that the deep ocean is warming, with Antarctic bottom water carrying a temperature signal into the abyss. The organisms of the Hadal zone, adapted to a world of near-constant frigid temperatures, may face a thermal stress that arrives long before a submersible ever photographs them, shifting their distribution and metabolic rates in ways we can currently only guess at. Another unresolved narrative concerns the very rhythm of life in the trenches, and whether the food webs there are stable or driven by sudden geological pulses. The classic view imagined a steady, gentle rain of marine snow sustaining a sparse but constant community, yet recent observations suggest a far more episodic reality. Seismic events like the 2011 Tohoku earthquake triggered turbidity currents that swept vast quantities of organic carbon into the Japan Trench, fueling a rapid bloom of microbial and animal activity. This raises the tantalizing possibility that the deep Hadal ecosystem is not a steady-state system at all, but a landscape of quiet famine punctuated by geological feasts, a cycle we are only just beginning to understand. In the deepest furrows of the ocean, nearly 11,000 meters below the surface, The pressure exceeds 1,000 atmospheres, and sunlight has never been more than a myth. Here, in the Hadal Zone, cameras have captured snailfish swimming with quiet deliberation and amphipods scavenging the sediment, their bodies engineered for a world that ought to crush and starve them. The discovery that life does not merely endure, but actively thrives in these trenches dismantled a long-held assumption that habitability requires a gentle envelope of moderate conditions. It forced a fundamental recalibration, revealing that the biochemical boundaries of life are far more elastic than we had imagined. The creatures of the Hadal realm are not passive survivors. They are specialists shaped by the very extremes we once considered hostile. Piezophilic organisms, whose cellular machinery actually requires high pressure to function, have taught us that pressure is not a stressor to be tolerated, but a parameter to be optimized. Their membranes remain fluid where ours would crystallize, and their proteins fold correctly under a weight that would denature surface enzymes. This quiet revolution in microbiology has expanded the definition of a habitable environment from a narrow set of Earth-like norms to a spectrum of possibilities where liquid water, a chemical gradient, and time might be the only universal prerequisites. The implications ripple outward from the ocean floor to the icy shells of distant moons. Europa, orbiting Jupiter, conceals a global ocean beneath a frozen crust, and models suggest the pressure at its seafloor could mirror the conditions found in the Mariana Trench. It is a realm of permanent darkness, isolated from the sun's energy and locked at temperatures just above the freezing point of salt water. The Hadal Zone thus becomes a tangible analog, offering a working hypothesis for how an ecosystem might organize itself in a sunless, pressurized ocean on another world. The study of psychrophilic microbes, those adapted to life near the freezing point of water, alongside piezophiles, now directly informs the search for life on icy moons. Laboratory experiments have shown that terrestrial deep-sea bacteria can not only survive, but replicate under simulated Europa conditions, drawing energy from the oxidation of iron or sulfur compounds. This research reframes the absence of sunlight not as a barrier, but as a scenario that simply selects for chemosynthetic food webs, powered by the planet's own internal chemistry. The instruments we send to Enceladus and Europa are being calibrated to detect the same subtle signatures of anaerobic metabolism first cataloged in the clays of oceanic trenches. Earth itself has a quiet habit of overturning our certainties. We once declared the boiling waters of hydrothermal vents too hot, the hypersaline brines of the deep Mediterranean too salty, and the kilometers of solid rock beneath our feet too devoid of energy for life. In each case, we were wrong. The planet kept presenting environments that our theories had labeled uninhabitable, and in each one, organisms were found not just clinging to existence but woven into complex, enduring communities. The Hadal Zone is simply the latest and most profound in a long series of reminders that our terrestrial intuition is a poor guide to the possible. There is a philosophical weight to living on a planet that continues to exceed its own definitions. Every time we lower a camera or a sampling bottle into a realm we have declared sterile, and life looks back at us, we are confronted with the limits of our imagination. The trenches are not an anomaly. They are a statement that the conditions for life are not a checklist of comforts, but a conversation between geochemistry and deep time. In the silent blackness of the Hadal, the Earth whispers a possibility that we are only beginning to understand, that the universe may be far more alive than we have ever dared to assume. Far beneath the surface of the southwestern Pacific Ocean, east of the Tongan archipelago, the seafloor plunges into a vast scar known as the Tonga Trench. Here, at a location called Horizon Deep, soundings have recorded depths of approximately 10,882 meters, making it the second deepest point in the world's ocean. Only the Challenger Deep in the Mariana Trench lies further down, yet this submarine canyon holds its own remarkable secrets. The trench is born from a titanic collision where the Pacific Plate thrusts violently beneath the Indo-Australian Plate. This subduction zone is among the most seismically active on Earth, generating frequent earthquakes and feeding a chain of highly active volcanoes that rise from the abyss to form the Tongan Islands. The ceaseless geological drama reshapes the landscape of the deep and fuels the chemical richness of the surrounding waters. Unlike many Hadal trenches that sit far from fertile surface zones, the Tonga Trench lies in close proximity to shallow, sunlit reefs and lagoons. This remarkable geography means that an unusually dense rain of organic particles, dead plankton, and other biological debris sinks rapidly from the productive island margins into the deep. The trench floor, though locked in perpetual darkness, receives a generous supply of food that sustains a surprisingly vibrant community of life. In these crushing depths, the creatures that thrive are distinct from those found in the Mariana Trench thousands of kilometers to the northwest. Specialized snailfish with translucent bodies and eel-like tails navigate the freezing gloom alongside giant amphipods that scavenge the nutrient-rich sediments. Each species represents a lineage shaped by the unique chemical signature, pressure regime, and food web of this particular chasm, isolated from its neighbors by vast abyssal plains. When scientists compare the fauna of the Tonga Trench with that of the Mariana, Kermadec, or Peru-Chile trenches, a profound pattern emerges. The Hadal Zone is not a single continuous habitat, but a string of separate islands of extreme depth, where the direction of currents, the distance from land, and the productivity of the surface waters above dictate which organisms can colonize and adapt. The Tonga Trench, with its volcanic warmth and abundant organic input, stands as a living laboratory for understanding how geographical isolation sculpts life in the deep. Such parallel studies reveal that each trench is a world unto itself, hosting an ecosystem that reflects millions of years of solitude and evolution. The darkness of the Tonga Trench echoes with the quiet rhythms of a community that has never known light, a delicate balance sustained by the connection between the volcanic islands above and the deep Hadal plain below. Listening to this silent world, we begin to appreciate that the ocean's deepest realms are not simply empty voids, but rich tapestries woven from the threads of Earth's immense geological and biological history. Beneath the vast blue of the South Pacific, the seafloor falls away into a realm of absolute darkness and crushing pressure. The Kermadec Trench stretches for over 1,000 kilometers north of New Zealand, plunging to a depth of 10,047 meters at its deepest point. This immense scar in the Earth's crust is the fifth deepest oceanic trench on the planet, a hidden world as remote as the surface of the moon. For decades, New Zealand has quietly established itself as a leading force in Hadal research, the study of ocean depths below 6,000 meters. The National Institute of Water and Atmospheric Research, known as NIWA, has mounted repeated expeditions to the Kermadec Trench, deploying sophisticated camera landers and sampling devices from the research vessel Tangaroa. These voyages have returned remarkable images of thriving life in the trench, from swarms of scavenging amphipods to delicate snailfish gliding over the sediment. A 2017 survey of the trench's amphipod populations delivered a discovery that was as sobering as it was surprising. Scientists sampling tiny crustaceans from the abyssal mud found polychlorinated biphenyls, or PCBs, and polybrominated diphenyl ethers, common flame retardants, at staggering concentrations. The levels were measured at up to 50 times greater than those recorded in crabs from the heavily polluted Liao River system in China, one of the most contaminated waterways in the world. This finding was a stark revelation of how thoroughly human industrial activity has infiltrated the global ecosystem. These chemicals, though banned decades ago, bind to sinking particles of organic matter and microplastics, drifting down through the water column to accumulate in the deepest living organisms. The trench effectively acts as a final sink, concentrating pollutants from distant continents and proving that no part of the ocean remains untouched by our chemical footprint. The fate of this extraordinary environment has been caught up in a long-running debate over the proposed Kermadec Ocean Sanctuary. The sanctuary, which would protect 620,000 square kilometers of pristine ocean including the trench, was first announced in 2015 but has since stalled amid political and commercial wrangling over fishing, mining rights, and Maori interests. For scientists, the outcome carries direct implications for research access, as a fully gazetted sanctuary would introduce a permitting framework that could both safeguard the ecosystem and add layers of administrative oversight to future expeditions. In the quiet depths of the Kermadec Trench, life endures in a delicate balance, carrying the chemical signatures of a distant human world. New Zealand's sustained scientific effort has illuminated this hidden frontier, while also revealing the profound reach of our planetary impact. The ongoing story of the trench is a reminder that the deepest places on Earth are not isolated, but intricately connected to the surface by the currents and choices that shape the entire ocean. Deep beneath the surface of the North Pacific, the Japan Trench carves a dark arc parallel to the eastern coast of Honshu. At its deepest point, the trench plunges to 9,780 meters, a realm of immense pressure and near-freezing temperatures. This is a Hadal zone, named for the realm of Hades, where life exists in extreme isolation, and the seafloor is a vast archive of geological time. On the 11th of March 2011, the seafloor convulsed as a magnitude 9.0 megathrust earthquake ruptured the fault zone beneath the trench. The violent displacement of the Pacific Plate triggered a colossal tsunami, but it also sent massive sediment avalanches known as turbidites, cascading down the trench slopes. These dense clouds of mud and sand swept across the Hadal Plain, scouring the seabed and stripping it of its accumulated biological legacy. For deep-sea biologists, the earthquake became an unplanned natural experiment. A Japanese research team had precisely mapped and sampled the trench floor in the years leading up to 2011. When they returned months after the disaster, their remotely operated vehicles revealed a landscape transformed. The soft sediment, once a habitat for a sparse but stable community of animals, had been completely erased, leaving behind a sterile, rocky floor and an ecosystem in collapse. The first signs of life to return were not visible to the naked eye. Thin, white and gray bacterial mats, fueled by chemical energy seeping from the freshly exposed sediments, began to spread across the bare rock. These microbial pioneers were the primary colonizers, stabilizing the surface and creating the first organic matter. Slowly, they were followed by small scavenging amphipods, tiny crustaceans that drifted in from the surrounding water to pick at the microbial growth. Over the following years, the careful documentation of recovery continued. The amphipod populations gradually increased, and a few other hardy species, such as small polychaete worms, began to appear. The community was not rebuilding to its former state, but rather starting from scratch, a slow succession in one of the least accessible places on Earth. The pace of renewal is measured in decades, not years, and the trench will likely take centuries to fully regain its pre-2011 character. This rare glimpse into a post-catastrophe reset reveals the deep rhythm of the Hadal world. The Japan Trench is a system shaped by violent disturbance intervals that are spaced hundreds to thousands of years apart. Between these events, life slowly assembles into a fragile climax community. Over geological time, this cycle of annihilation and renewal has driven the evolution of species uniquely adapted to a world poised between total erasure and patient, enduring recovery. The Hadal Ecosystem Studies Program, known as Hades, was a pioneering multi-institutional investigation into the deepest reaches of the ocean, running from 2014 to 2017. Funded by the National Science Foundation, it brought together scientists from the University of Hawaii, the Woods Hole Oceanographic Institution, and several other American research bodies. Their aim was to conduct the first truly systematic, comparative study of Hadal trenches, which are the narrow, deep fissures plunging beyond 6,000 meters. To achieve this, Hades deployed free-falling instrument platforms, or landers, simultaneously across 5 trenches in the Pacific Ocean. These included the Kermadec, Tonga, New Hebrides, and Mariana trenches, spanning a vast geographic arc. Each lander carried baited cameras, traps, and sensors, allowing the team to record life, collect specimens, and measure physical parameters at matching depths in different trenches for the very first time. One of the program's most striking revelations was the consistency of biological communities in these isolated habitats. Despite the immense distances and the seafloor ridges separating each trench, the same broad suite of organisms appeared again and again at equivalent depths. A particular species of scavenging amphipod, Hirondelia gigas, dominated the deepest points from the Mariana Trench to the Kermadec Trench, suggesting powerful environmental filtering rather than random dispersal. The researchers meticulously pieced together a functioning food web in a place once thought to be a biological desert. They traced the energy flow from the gentle rain of marine snow, the primary producers drifting down from the sunlit surface, to the voracious swarms of amphipods that act as the Hadal scavengers. Above them, the team documented predatory snailfish and decapods, demonstrating that even at 8 or 10,000 meters, a complete trophic structure exists, sustained almost entirely by surface productivity. Hades data also provided a new understanding of how these distant trenches might be connected. Genetic analysis of key species indicated that the midwater realm, the vast column of water between the surface and the seafloor, acts as a hidden corridor. The larvae of Hadal snailfish, for example, do not simply crawl along the bottom, but appear to spend time in the pelagic zone, allowing for mixing and gene flow between populations that are separated by thousands of kilometers of seemingly impassable abyssal plain. The program's meticulous cataloging of life and environmental conditions has established an irreplaceable baseline for the Hadal zone. As interest in deep-sea mining, climate-related shifts in surface productivity, and even plastic pollution extends into these remote trenches, the Hades dataset stands as a quiet, authoritative record of what was there before any significant human disturbance. It is a foundational ecological portrait of the ocean's final frontier, gathered just in time. In the crushing stillness of the Hadal zone, sound behaves in ways that defy surface intuition. The immense pressure and cold temperatures alter the very structure of seawater, causing sound waves to accelerate to nearly 1,500 meters per second. This speed, combined with a natural phenomenon known as the SOFAR channel, a layer of minimum sound velocity where waves are refracted and trapped, creates a deep-sea waveguide. A single vibration can travel vast distances across ocean basins, funneled horizontally through the darkness with barely a whisper of energy lost. During the Cold War, the United States military deployed a classified network of seafloor hydrophones called SOSUS, originally designed to track Soviet submarines. In the quiet depths, operators began to hear a chorus of unidentifiable sounds, clicks, moans, and rhythmic pulses that were clearly not man-made. These mysterious signals, some of which originated from the very deepest parts of the ocean, were initially logged as geophysical anomalies or biological interference. The spy network had inadvertently become the first global ear on the Hadal zone, revealing a hidden acoustic world that had been completely unknown to science. The songs of great whales, produced by animals that never descend into the Hadal realm, are delivered to the trench floor by the very physics of the deep sound channel. A blue whale's low-frequency moan, barely audible to a diver in the photic zone, is funneled downwards and arrives at a Hadal lander as a resonant, room-filling hum. The sound is stripped of the crackling surface noise and biological chatter of the upper ocean, arriving with a spectral purity that makes it seem as though the singer is drifting just beyond the lander's frame. Today, that same acoustic curiosity is carried into the abyss by autonomous Hadal landers, platforms that fall freely to the seafloor and lie in wait for months. These landers are equipped with sensitive passive acoustic recorders, hydrophones that can capture the faintest whisper of sound from the surrounding water column. Deployed in trenches from the Mariana to the Kermadec, they sit patiently on the sediment, their memory cards filling with digital representations of a world without light. The retrieved recordings shatter any notion of a silent deep. The soundscape is a dense tapestry of natural noise, from the high-frequency crackle of snapping shrimp, whose colonies extend far deeper than anyone imagined, to the echolocating clicks of deep-diving cetaceans and the mournful calls of baleen whales. Interwoven with this biological chatter are the deep, percussive groans of the earth itself, the grind of tectonic plates, the rumble of distant landslides, and the seismic whisper of magma moving beneath the trench floor. Acoustic monitoring has become a vital instrument for observing the unobservable. It reveals a daily rhythm of migration, as animals rise and fall in the water column, and a seasonal pulse of biological activity linked to the sunlit world far above. Each sound is a data point, confirming the presence of life, mapping its movements, and exposing the intimate behaviors of creatures that have never been seen alive. In the permanent night of the Hadal zone, the ear now sees what the eye cannot. In the deepest fractures of the ocean floor, where the water column exerts pressures that would crush a human instantly, life persists in a state of extreme biochemical adaptation. Here, bacteria known as piezophiles assemble enzymes that maintain their delicate three-dimensional shapes not despite the crushing weight, but because of it. A conventional enzyme from the surface world would collapse and unravel under such force, its active site distorted beyond function. Yet a Hadal enzyme folds with a compact, dense core that uses pressure as a stabilizing influence, often operating optimally at temperatures just above freezing where ordinary reactions would slow to a near halt. This pressure tolerance makes piezostable enzymes extraordinarily valuable for industrial processes that occur at the thermodynamic extremes where standard proteins fail. In food processing, Cold active proteases and lipases from the deep sea can tenderize meat or clarify fruit juices without the high heat that degrades delicate flavors and nutrients. Pharmaceutical synthesis benefits from enzymes that catalyze intricate chemical steps at low temperatures and high pressures, preserving the unstable molecular structures of modern drug candidates. The biofuel sector looks to Hadal cellulases that dismantle plant biomass into fermentable sugars under conditions that reduce energy costs and prevent the contamination that plagues warm bioreactors. Beyond their catalytic machinery, Hadal bacteria produce a hidden library of novel metabolites, small molecules that are not found in any surface water relative. These organisms have spent millions of years evolving in solitude, exposed to a unique chemical environment rich in metals, methane seeps, and brine pools. The resulting secondary metabolites often possess unusual ring structures, halogen atoms, and bonding patterns that are entirely absent from the standard pharmacopoeia. This chemical novelty is exactly what drug discovery programs seek, because it increases the probability of finding a molecule that can bind to a human disease target in a completely new way. The precedent for such a search was set decades ago, though the most celebrated marine-derived drugs came from shallower waters. The chemotherapy agent cytarabine, used worldwide to treat acute leukemia, was inspired by nucleoside compounds isolated from a Caribbean sponge. An entirely different strategy emerged from the venom of a cone snail, yielding ziconotide, a peptide that blocks pain signals in the spinal cord with a potency 1,000 times that of morphine. These successes were not from the Hadal zone, but they illuminate the principle that organisms facing extreme biological pressures often evolve chemical defenses of immense therapeutic value. The Hadal trenches themselves, however, remain almost entirely unexamined for pharmaceutical treasure. The technical obstacles are formidable. Retrieving a sample from 8 or 10 kilometers down without it warming up and depressurizing during the ascent is a feat of engineering that only a handful of submersibles and landers can accomplish. Most of the resident microbes cannot be cultured in a standard laboratory, because removing them from their high-pressure habitat triggers a shock response that silences the very metabolic pathways a chemist would wish to study. As a result, the trenches are the least sampled biome on Earth for natural product discovery, a vast biological dark matter. The quiet promise of the Hadal zone lies in this very inaccessibility, because it has protected a reservoir of evolutionary experiments that the pharmaceutical industry has not yet screened. Advances in pressure-retaining sampling gear and metagenomic sequencing now allow scientists to access the genetic blueprints of these microbes without ever growing them in a dish. The first glimpses of their biosynthetic gene clusters suggest the capacity to build molecules that could disrupt cancer cell division, disarm antibiotic-resistant bacteria, or calm misfiring neurons. The search is only just beginning, and it unfolds in the slow, deliberate rhythm of a world that has never known sunlight. In the deepest ocean trenches, life exists in a realm of crushing pressure and perpetual darkness. Here, scientists have uncovered a remarkable pattern. Certain species are found in only one trench and nowhere else on Earth. This phenomenon, known as Hadal endemism, reveals that each trench functions as a biological island, isolated by the vast abyssal plains that separate them. The Mariana snailfish, for instance, lives exclusively in the Mariana Trench, while its relatives inhabit other specific trenches. The trenches are separated by thousands of kilometers of seafloor, creating barriers that few organisms can cross. Over evolutionary timescales, populations become genetically distinct, leading to the formation of new species unique to each trench. Deep-sea amphipod crustaceans, such as those in the genus Hirondelia, often show trench-specific distributions, suggesting that isolation has been a powerful engine of speciation in the Hadal zone. By comparing the genomes of Hadal animals with their shallow water cousins, researchers are deciphering the genetic underpinnings of life under extreme pressure. Studies on the Hadal snailfish have revealed modifications in genes associated with cell membranes, bone structure, and protein stability. One key finding is the enhanced expression of genes that produce trimethylamine N-oxide, a chemical chaperone that protects proteins from being crushed. These genomic adaptations allow Hadal creatures to thrive where others would perish. The use of trimethylamine N-oxide, or TMAO, as a pressure countermeasure appears to have evolved independently in several Hadal lineages. Snailfish, grenadiers, and even some amphipods all accumulate high levels of TMAO, yet their evolutionary paths to this solution diverged long ago. This convergent evolution underscores the fundamental challenge of pressure and the limited biochemical avenues available to overcome it. The repeated emergence of TMAO-based adaptation highlights nature's tendency to find the same elegant solution under similar extreme selective pressures. The Hadal environment has remained remarkably stable over geological time, with near-freezing temperatures, no sunlight, and immense pressure. In such a changeless world, evolution has proceeded at a slower rhythm, often preserving ancient body plans. Some Hadal organisms, like the monoplacophoran mollusks, are living fossils that have barely changed in hundreds of millions of years. The Hadal record suggests that extreme stability can lead to both exceptional longevity of lineages and the slow, steady rise of novel adaptations. Hadal science is reshaping our understanding of evolution's limits and possibilities. It reveals that isolation can create hotspots of endemism even in the deep sea, that genomic innovation enables life to colonize the most hostile places, and that convergent evolution is a recurring theme in the abyss. As we explore more of these frontiers, the trenches may hold further clues about life's resilience and the deep history of our planet. Far below the reach of sunlight, a slow perpetual rain of organic particles drifts downward through the water column. This marine snow, composed of dead plankton, fecal pellets, and other biological debris, acts as a conveyance for persistent organic pollutants that entered the surface ocean decades ago. Because these chemicals are hydrophobic, they readily bind to the lipids and carbon within sinking particles, hitching a ride into the abyss. At a depth of 10,000 meters in the Mariana Trench, small scavenging crustaceans called amphipods carry a toxic legacy that surpasses that of coastal predators. The pollutant load in these Hadal amphipods, particularly of polychlorinated biphenyls, or PCBs, has been measured at concentrations higher than those found in dolphins swimming in the North Pacific. This seeming paradox is explained by the extreme environmental conditions. The cold temperatures and crushing pressures slow the animal's metabolism, leading to a longer lifespan and a greater accumulation of contaminants that are already concentrated in the carrion and detritus sinking from above. The Hadal trenches themselves function as a final repository for the ocean's drifting particles. The steep topography of these subduction zones funnels and traps marine snow that has escaped microbial degradation in shallower, sunlit waters. Once settled into the sediment of these deep-sea basins, the organic matter and its chemical passengers are effectively sequestered from the processes that might otherwise recycle them back into the water column. The story of anthropogenic contamination does not end with invisible chemicals. In sediment cores extracted from these same lightless plains, researchers have identified microplastic fibers at densities reaching 2,000 pieces per liter. The finding confirms that the smallest fragments of our synthetic waste are now entrained in the same global circulation patterns that deliver fine sediment to the deepest geological formations on Earth, marking the seafloor with a quiet, fibrous imprint of the Anthropocene. The discovery of human-manufactured chemicals at the planet's deepest point forces a profound reconsideration of the word pristine. There is no place on Earth that remains untouched by our industrial activity. The Hadal Zone, once imagined as a realm of absolute purity, now stands as a silent monument to the reach of human influence. The contamination reveals that the ocean's layers are not separate worlds, but a continuous, connected system where the surface and the depths are intimately linked. This evidence carries urgent implications for the governance of international waters. The accumulation of persistent pollutants in the deep sea demonstrates that the current frameworks for chemical management and waste disposal are insufficient to protect the planet's most remote ecosystems. It underscores the need for a more integrated, precautionary global policy that treats the entire ocean as a single, interconnected body and holds that what we release into the surface waters is not truly gone, but merely on a long, slow journey to the bottom of the world. The Hadal trenches do not simply deepen the ocean. They redraw the boundaries of what life can be. Every expedition below 6,000 meters finds organisms thriving at pressures that were once thought to crush proteins into glass, using metabolic pathways that rewrite the rules of biochemistry. The fish that swim where the water column exerts 1,000 atmospheres do so with enzymes that fold correctly only under that crushing weight, challenging the notion that extreme environments are merely endured. These are not survivalists clinging to a fringe. They are entire ecosystems, from scavenging amphipods to microbial mats, functioning with a complexity that suggests the deep sea is not a desert, but a vast, slow-moving world whose logic we are only beginning to interpret. What emerges from each new discovery is a quiet invitation to reconsider the very nature of certainty. The Hadal Zone keeps proving that the planet's deepest places are not a museum of immutable conditions, but a living laboratory where assumptions dissolve. This is science at its most productive, a practice of continuous revision in which being wrong is not a failure, but a return to the state of not knowing from which actual understanding can grow. The ocean floor is a reminder that the Earth still holds a great deal of itself back, waiting for the moment when our instruments and our humility are ready. Somewhere in the darkness between the trench walls, the water moves with a slowness that cares nothing for the pace of surface life. The creatures there are not in a hurry, and the sediment accumulates grain by grain over centuries. Letting the mind settle into that kind of deep time is a way of accepting that not everything needs to be resolved tonight. The quiet down there is the same quiet that can fill a room when the last light is gone. A presence that asks nothing except that you stop trying to map the entire ocean at once. At 10,000 meters below the ocean surface, the weight of the water column above exerts a pressure approximately 1,000 times greater than atmospheric pressure at sea level. This translates to roughly 100 megapascals, a force equivalent to 100 million pascals pressing on every square meter. It is a realm defined entirely by this crushing, constant presence. Water itself is remarkably resistant to compression. Even under the full Hadal load, its volume decreases by only about 5%. Gas-filled cavities, however, face a different fate. Any air pocket, such as a fish's swim bladder, would be collapsed instantly and completely, rendering such structures useless in the deep. Some of the most successful inhabitants of the Hadal zone are piezophilic bacteria, organisms that not only tolerate extreme pressure, but require it. Their optimal growth occurs at pressures between 700 and 1,000 atmospheres, the very conditions found in the trench. When brought to the surface, their internal proteins and membranes lose their functional shape, and the cells perish. To maintain cellular integrity, deep-sea organisms employ protective molecules known as piezolites. Trimethylamine oxide, or TMAO, is a key compound that stabilizes proteins under pressure by reinforcing the hydrogen bonding network of water. Other piezolites, such as certain sugars and amino acids, work in concert to prevent the crushing force from distorting the delicate three-dimensional structures of enzymes and other biomolecules. These adaptations come at a cost. They are irreversibly tailored to the high-pressure habitat. When Hadal organisms are raised toward the surface, the rapid decrease in pressure disrupts their protein complexes and cell membranes. Their metabolic pathways, calibrated for a pressurized world, run out of control, and most die long before they ever see the light of the sun. The ascent itself becomes a fatal journey. The piezolites that once protected them may become destabilizing, and the very enzymes that sustained life begin to fail. This extreme specialization is why the Hadal realm remains one of the least explored frontiers on Earth. Its inhabitants are prisoners of the deep, bound forever to the immense quiet of the trench. Deep within the ocean, beyond the reach of sunlight, the Hadal zone begins where the seafloor plunges into narrow trenches. Here, in the deepest places on Earth, the water temperature hovers between a constant 1 and 4 degrees Celsius. This thermal stability is a hallmark of the Hadal realm, a world insulated from the seasonal fluctuations that stir the surface. Year after year, the cold remains unyielding, a quiet backdrop to life at extreme depth. The combination of this perpetual cold and the crushing pressure, which can exceed 1,000 atmospheres, profoundly slows the pace of chemical reactions. Molecules move with less energy, and biochemical processes that sustain life proceed at a fraction of their surface speed. Metabolic rates in Hadal organisms are therefore exceptionally low, a necessary adaptation that conserves energy in an environment where food is scarce. Life here moves to a rhythm defined by patience and deep, slow time. To thrive in such cold, the creatures of the Hadal zone have evolved at a cellular level. Their membranes are built with a high proportion of unsaturated fatty acids, which remain flexible and fluid even at temperatures that would cause other biological membranes to stiffen like cold butter. This biochemical strategy ensures that vital functions, such as nutrient transport and cellular communication, can continue seamlessly in the dark and the chill. It is one of the most fundamental invisible adjustments that makes Hadal life possible. The cold that fills these trenches has a distant origin, a direct connection to the Antarctic. Along the frozen margins of the Southern Ocean, seawater is chilled and becomes exceptionally dense as it mingles with brine rejected from forming sea ice. This dense water sinks and begins a slow, centuries-long journey northwards along the seafloor, forming the Antarctic bottom water that ventilates the abyss and spills into the deepest trenches. The Hadal Zone is, in a very real sense, the final resting place of Antarctic winter. Today, however, this deep thermal regime is beginning to shift. Measurements taken over recent decades show that abyssal water masses are warming measurably, a fingerprint of climate change reaching even the most remote corners of the planet. The rate of warming is small in absolute terms, but it is significant for water that has been thermally stable for millennia. This slow infusion of heat is the first ripple of a surface disturbance propagating into the deep. For Hadal communities, any sustained temperature increase will alter the fundamental physical conditions to which their biochemistry is exquisitely tuned. A rise of just a few tenths of a degree could raise metabolic rates, increasing the demand for food in an already nutrient-poor environment. The delicate balance of membrane fluidity, evolved for a narrow thermal window, may be challenged, and the oxygen concentration of these deep waters, already low, could decline further. The quiet, constant cold that shaped life in the trenches is no longer a given, and its gradual warming signals a profound shift for one of Earth's most extreme and least understood ecosystems. The Hadal Zone, the deepest region of the ocean from 6,000 to 11,000 meters, exists almost entirely beyond any single nation's jurisdiction. The UN Convention on the Law of the Sea, or UNCLOS, defines these waters as the high seas and the seabed as the area, meaning no state can claim sovereignty. Under UNCLOS, scientific research in international waters is a freedom of the high seas, but it must be conducted with due regard for other uses and for the marine environment. The International Seabed Authority, established by UNCLOS, manages the mineral resources of the deep seabed, including the abyssal plains and potentially the Hadal trenches. It has issued exploration contracts for polymetallic nodules and crusts, but mining operations could release sediment plumes and disturb ecosystems that scientists have only begun to map. The authority is now developing exploitation regulations, and the Hadal trenches, with their unique life forms, remain vulnerable to such industrial activity. In 2023, the High Seas Treaty, formerly the Agreement on Biodiversity Beyond National Jurisdiction, offered new protections for international waters. It requires environmental impact assessments for activities like deep-sea mining and creates mechanisms for establishing marine protected areas. These tools could shield Hadal habitats from degradation, though the treaty has not yet entered into force, requiring ratification by 60 nations. Access restrictions under UNCLOS and the High Seas Treaty affect how Hadal research is conducted from ships of signatory nations. A research vessel flagged to a party to the treaty must comply with its environmental impact assessment rules before deploying submersibles or samplers. This can delay expeditions, but it also ensures that Hadal studies are planned with biodiversity conservation in mind. Data sharing agreements between nations shape the collective understanding of Hadal ecosystems. Many deep-sea research programs require that data be deposited in open-access databases, such as the Ocean Biogeographic Information System. This transparency allows scientists from developing and developed nations alike to analyze trench biodiversity, though political sensitivities over mineral rights can sometimes slow the exchange of precise location data. The intersection of Hadal science and international law is a negotiation between discovery and stewardship. As researchers descend into the deepest trenches, legal frameworks like UNCLOS, the High Seas Treaty, and the International Seabed Authority's regulations dictate what can be taken, what must be shared, and what must be preserved. The future of the Hadal Zone depends on how these laws evolve to match the pace of human exploration. In the years following the Second World War, a quiet revolution stirred beneath the ocean's surface. The Danish Galathea deep-sea expedition, which sailed from 1950 to 1952, set out with a specific and audacious goal: to conduct the first systematic search for life in the deepest parts of the ocean, the Hadal trenches. Using heavy trawls and dredges deployed on miles of wire, the crew of the research vessel Galathea patiently sifted the abyssal plains and the sheer walls of submarine canyons. It was a methodical, grinding effort, a stark contrast to the speculative theories that had long denied life could exist under such crushing pressure and absolute darkness. The expedition's most dramatic success came in the Philippine Trench, where the dredges bit into the seafloor at depths exceeding 10,000 meters. From these unprecedented hauls, the scientists carefully retrieved tangible proof of a hidden world. They documented sea anemones clinging to stones, bristled polychaete worms, small bivalve mollusks, and a suite of bacteria thriving in the cold, pressurized sediment. Each specimen, however fragile, was a direct refutation of the old certainties, hauled up from a realm that had been considered a sterile desert. The leader of the expedition, the Danish oceanographer Anton Brun, moved swiftly to consolidate these findings into a definitive scientific statement. His publications, rich with meticulous descriptions and photographs, presented an irrefutable case that life not only existed, but was adapted to the full vertical extent of the ocean. The azoic hypothesis, a lingering Victorian notion that the ocean floor below a certain threshold was lifeless, was permanently shattered. Brun's work replaced this blank void with a vivid, continuous biological frontier extending the biosphere to the deepest point on Earth. Yet for all its triumphs, the technology of the time imposed a profound limitation on what could be known. The trawl nets, winched down on steel cables, were blind instruments that gathered specimens into a bag and then hauled them through a disorienting vertical column of water. During the ascent, which could take many hours, the delicate gelatinous creatures, the soft-bodied fish, and the fragile interconnections of the deep-sea community were largely lost. The animals that arrived on deck were the survivors, a biased sample of the robust and the resilient, their tissues and chemistry already altered by the catastrophic change in pressure and temperature. The physical legacy of the Galathea expedition now rests in the quiet, climate-controlled collections of the Natural History Museum of Denmark in Copenhagen. Thousands of glass jars and preserved specimens, many still unidentified, form a library of deep-sea life frozen in time. Today, researchers approach these same samples with modern genomic tools, extracting DNA to reconstruct evolutionary histories and to understand the molecular adaptations that allow life to function under extreme pressure. The original expedition gathered the raw material, but the deep analysis, it turns out, was only just beginning. The Galathea voyages transformed the Hadal Zone from a mythical abyss into a tangible biological province. By proving that life could be systematically collected from the deepest trenches, the expedition established the fundamental techniques and the compelling questions that would define the field. It was the bridge from an era of speculation to the modern era of Hadal research, where landers, submersibles, and genetic sequencers now continue the meticulous work that the Danish trawls began in the cold, dark heart of the Philippine Trench. Bacterial diversity in Hadal sediments differs markedly from that of the abyssal plains and shallow coastal shelves. The crushing pressures, near-freezing temperatures, and isolation of the trenches select for microbial communities dominated by groups such as Chloroflexi, Actinobacteria, and Planktomycetes, which are far less abundant in sunlit, wave-mixed seabeds. This vertical stratification means that the Hadal Zone hosts a disproportionate share of evolutionary novelty, with many lineages found nowhere else on Earth. At the heart of the Hadal food web, piezophilic bacteria are uniquely equipped to dismantle the most obstinate organic compounds that sink from the surface. Lignin and cellulose, the structural scaffolds of wood and plant debris, resist rapid decay in shallow waters and can drift for millennia before settling in a trench. Once there, pressure-adapted enzymes allow these microbes to cleave the tough molecular bonds, unlocking carbon that would otherwise remain sequestered in a dormant state. Metagenomic surveys of Hadal sediments have revealed an astonishing catalog of life. In the Mariana, Kermadec, and Atacama trenches, environmental DNA sequencing has identified thousands of bacterial genera that are entirely new to science, representing deep branching lineages with no close relatives in the known biosphere. Each new sample pulled from the seafloor continues to expand the tree of life, hinting that the trenches are vast reservoirs of undescribed metabolic potential. The nitrogen cycle in these deep furrows operates through a sophisticated microbial network that directly influences global ocean chemistry. Denitrifying bacteria convert dissolved nitrate into inert nitrogen gas, which then diffuses out of the sediment and eventually leaves the ocean. This process strips the deep sea of a nutrient essential for photosynthesis, and the cumulative activity of Hadal denitrifiers contributes measurably to the planetary budget of fixed nitrogen. What the microbial communities reveal about carbon remineralization challenges the assumption that decay simply slows to a halt with depth. In the Hadal zone, the rate of organic carbon processing can be surprisingly high, driven by heterotrophic bacteria that thrive on the fresh supply of material funneled down the trench slopes. However, because much of this carbon is rapidly entombed in accumulating sediments, the net effect is a prolongation of carbon storage on geological timescales, locking it away from the atmosphere for millions of years. Taken together, the Hadal microbiome functions as a hidden engine that completes the ocean's nutrient circuits. It transforms the most recalcitrant leftovers of surface life, sculpts the marine nitrogen inventory, and governs the ultimate fate of sinking carbon. These quiet, lightless ecosystems breathe at a rhythm dictated by the slow rain of particles from above, reminding us that the deepest places on the planet are not stagnant graves but living, cycling interfaces between Earth's crust and water. Below 6,000 meters, the rules change. They have always changed. Every instrument we have lowered into that depth has returned with something we did not expect. The science of the Hadal zone is not a story of accumulating certainty. It is a story of accumulating revision, of assumptions rebuilt and replaced, of life found where life was declared impossible. That revision is still happening tonight, in the dark of the Mariana Trench, where something moves through pressure we cannot survive, in a cold we cannot enter, eating what falls from a world it has never seen. The trench is patient. It will still be there tomorrow, and it will still have more to show us than we have instruments to find.